Alright, so in this video I wanted to go over these two theorems that are called the Pappus-Guldinus theorems, and they may seem unrelated to what we're doing, which is basically concentrating on the idea of centroids of areas or lines or volumes, but they are related because it's a new way to calculate a surface area of revolution or a volume of revolution, where in the calculation of these quantities you're actually using centroids. So let's take a look at the theorems. So the first theorem allows us to find the surface area of revolution using the centroid of the line that's revolved around the axis. So the idea is you start with some sort of line segment, and if you revolve it around an axis, you're going to create a surface area. And so the idea is, of course, there are ways to calculate this surface area, but this particular way is actually going to be using the centroid of the original line. And the expression that we end up with is that the area is equal to 2 pi. Now 2 pi represents the angle that the line was revolved around. So if you go completely around, of course, it would be 2 pi. You could also use this expression for a smaller angle, and instead of 2 pi, you would just enter the value of that angle in radians. And then it's going to be equal to the centroid of the line and then the length of the line. So let's see how this is going to work. In this picture right here, we actually see a strip of the surface area, and we're trying to express how we would calculate the area or what increment of area this would represent. So you can see that the length or the height of the strip is dl, and it's a distance from the x-axis equal to y. So think about that strip. This is basically forming a circle when you're revolving around the x-axis. So the total area of that strip could be calculated using the circumference of the circle, which would be 2 pi y, times the height of the strip, which is dl. So that is how we would express the increment of area that we see in that picture. And of course, the area would be calculated by doing this integration. Now, of course, we could do this integration, but I want you to think about the fact that the definition of the y-centroid of that line actually involves that very same integral. So you see that in the definition of the y-centroid, we see the integral of y dl. So we could actually rearrange this and see that the integral of y dl could be written in terms of the centroid and the length of the line. And so we're going to do that substitution here, and then y centroid times the length, and there we go. We have the first theorem. So you see how that worked? And in a sense, it's not that you have to prove it every time, it's just showing you why this is true, but this would be another way that we could calculate the area of the surface area of a revolution with just using the idea of centroids. Now the second theorem is pretty similar, but this time we're going to take an area and revolve it around the axis. And when we do that, we create a solid volume. So the volume, according to the theorem, would be equal to 2 pi. Once again, that represents the angle that we've revolved the area around. If you don't go the whole way around, you could just replace 2 pi by the angle that represents how much you revolved it, and then times y prime, y bar, where y is the centroid of the area that we revolved, times the area. So you can see that it has a really similar expression. It's just that we're talking about a different type of calculation. Now over here on the far right, we see the expression where we can kind of get a sense of how we might calculate the dV, and they've taken these circular rings, which are 3D, so I'm not sure what to call them. They're kind of like washers. And you can see that the cross-sectional area of the ring we can call dA, and then the distance around would be 2 pi y. So the dV would be equal to 2 pi y times dA. And so if we integrate both sides, again we get a very similar expression for calculating the volume, where we have this integral of y dA, and again just recognizing the fact that the centroid of the area that we started with would involve this same integral. And so if we rearrange this, we can say that another way to write our integral, which is in our calculation, could just be y bar times a. And so we can say that the volume could be calculated as 2 pi with the y centroid of the area times the area itself. All right? And so again, these are just ways that we can calculate these values, volume or area, using centroids. So I thought it would be if we looked at an example. Now, in this example, we're going to find the volume that we generate when we revolve the curve around the y-axis. Now, when we do that, this sort of represents the area that we're going to be working with. And another thing that I want you to think about, so we're saying volume is 2 pi. Now, because of the fact that this time we're revolving around the y-axis instead of the x-axis, means that we're going to be more interested in, we're not going to be basing it on the y centroid, but the x centroid. So it's going to be x centroid times the area. And this kind of sets me up here because this would represent my dA. And so let's just, first of all, calculate the total area that we're revolving around the axis using this increment here, which has a width of dx, and then the height is going to be the value of y at the top minus the value of y at the bottom. And we'll sort of get to the proper expression of that in a minute. So if I wanted to find the area that we've revolved around the curve, I'm going to take the integral of dA, which is y top minus y bottom times dx, and x goes from 0 to 1. Now, of course, you have to, the value, we can't use y's and integrate over x. So what is the y value at the top? Well, that's just 1, because this horizontal line represents the top, and the y value at the bottom is x squared. And so when I integrate that, I'm going to get x minus x cubed over 3, evaluated at 0 and 1, which is going to have a value of 2/3. Now, to find the x prime, we would do the integral of x dA over the area, which we already know what that is, so I'm not going to do that again. And so that would end up to be, we're going to, I guess, really remember that this is our dA, so we have x times 1 minus x squared dx over the area, which is the integral of x minus x cubed dx over the area. And so when we integrate that, we get x squared over 2 minus x fourth over 4, evaluated at 0 and 1. And the area is 2/3. So if I evaluate the top or the numerator of this fraction, it's going to be 1/2 minus 1/4 over 2/3. So it's 1/4, and then I'm going to just flip the bottom times 3/2. So it's 3/8 is my x bar. So let's put this information up above. I got 2 pi times 3/8 for my x bar. My area was 2/3. So we can see we can do some simplifying. And we end up with a volume of pi over 2. And so that's how we would actually use one of these theorems. All right, that's it.